Hello everyone and welcome to Control Engineering, Control Systems, Optimization and Dynamics tutorials. In these tutorials, we present real and applicable knowledge of control systems, signal processing algorithms, and optimization algorithms with special emphasis on the implementation of algorithms in C or C++ or Python. This particular tutorial is dedicated to the batch gradient method and its implementation in Python. The batch gradient method is also known as the steepest descent method or the gradient descent method. However, I'm using this name batch gradient method simply because in machine learning community, the steepest descent method or the gradient descent methods are usually known as batch gradient methods. In my future videos, I will also explain the stochastic gradient method. Now, some of you might stop me over here and ask me the following question. Why should we watch this tutorial when online we can find millions of tutorials covering batch gradient method and its Python implementation? Here's the answer. In this video tutorial, I provide the explanation of the batch gradient method from the control engineering perspective, which I believe is a very useful perspective for engineers and scientists. Moreover, I will only focus on practical aspects of this method and I will explain how to implement this method in Python. Before I start, here are a few important things that I would like to emphasize. First of all, those of you who are my subscribers or who follow this channel know by now that I always create a post that nicely summarizes everything that I will explain in this video. And consequently, here is the post. This post contains figures, all the explanations, and even Python codes. A link to this post is given in the description below. Secondly, it took me a significant amount of time, energy, and planning to create this post and this video tutorial. And consequently, I kindly ask you to press the like and subscribe buttons. Thank you very much. In my previous tutorial, whose link can be found in the description below this video, I introduced the concept of gradient. I defined the gradient and explained how to compute the gradient for this function that you can see over here. Then, I summarized two important properties of gradients. Here is briefly the first important property. The gradient is a vector whose value at a certain point is the direction and rate of the locally fastest increase of the function f. And this fact will be very important for developing the gradient descent method. Then, I also explained that gradient is actually perpendicular to the level curve of the cost function. And here's the sketch, here's the level curve, and here's the gradient. It's perpendicular to the tangent of the level curve of the cost function. These two properties are very important for proper understanding of batch gradient method. First, let us explain this word batch. The word batch refers to the data batch. That is, optimization problem in the batch form depend on a data batch that's symbolically represented over here, where x1, y1, x2, y2 until xn, yn are data points. y1 and x1 are scalars, and these two vectors consist of scalars. Now, for the purpose of explaining the batch gradient method, let us assume that the data points are related through a linear model. That's shown over here. We can assume that y is equal to the parameter θ1 multiplying x plus the parameter θ2. The parameters θ1 and θ2 are parameters of the linear model that we want to estimate. The previous equation is an ideal representation of a physical system or a process. For example, this model can represent a calibration curve of our sensor. For example, y can be a voltage and x is the physical variable that we are interested in observing from the measured voltage, such as distance, pressure, or temperatures. The parameter theta1 and theta2 are unknown parameters of the model that we need to estimate. In practice, this model is always corrupted by the measurement noise. The goal is to estimate the parameters theta1 and theta2 from the set of batch data x1, y1, x2, y2 until xn, yn. By substituting data points in the equation 22, we can obtain a system of equations given by the equation 23. If we substitute y1 and x1 in this equation, we obtain the first equation given over here. And notice over here that I have an additional n1 term, and this is basically a noise term, because in practice, measurement noise always degrades the sensor data, and consequently we will always have some stochastic noise in our measurement model. Similarly, if we substitute x2 and y2, we obtain this equation, and since we have n data points, we obtain the last equation. To estimate these parameters, we form the batch cost function given by the equation 24. This cost function is called the batch cost function simply because it depends on the batch data set. We form this cost function by taking the left-hand side of this equation, for example y1, and by subtracting theta1 multiplying x1 minus theta2. Then we square this term and we add the second term to the cost function. The second term will be simply y2 minus theta1 times x2 minus theta2. Again, we square this term and we add all the terms until the last term, that's equal to yn minus theta1 xn minus theta2. Notice here that n1, n2, and nn, that is the measurement noise entries, are unknown. After we form the batch cost function, we form the batch optimization problem that's shown over here. We want to minimize our batch cost function with respect to theta1 and theta2. This optimization problem is actually a linear least squares problem for which we can find the closed form solution. This is explained in my previous post, which can be found over here. In this post, I explained the method of least squares. I explained how to form the least squares problem and how to find the solution of the least squares problem in the closed form. And the closed form is given over here. However, in this tutorial, we will not use such a solution that is only applicable to linear least squares problems. Instead, we will use the batch gradient descent, that's also known as the gradient descent method or the steepest descent method, that is applicable to a much more general class of optimization problems that also includes nonlinear optimization problems and nonlinear least squares problems. For example, you can have here nonlinear terms, for example, theta1 multiplying theta2 or theta1 sinus theta2, and for these problems you cannot use the linear least squares problems. You need to use the steepest descent methods or some other methods. The main idea of the batch gradient descent method is to approximate the solution of the optimization problem iteratively. First of all, we group the optimization variables and we form this vector theta. Then the batch gradient descent method approximates the solution by propagating this iteration. And in this iteration, k is the iteration index, gamma is the step size, that's also known as the learning rate. This is a relatively small number, either selected by the user or selected by using special methods, such as line search methods. Here we assume that this number is constant and independent from the index k of the current iteration. However, this number can also depend on the current iteration. theta with the superscript k is the vector of optimization variables at the iteration k, and it's simply composed of the optimization variables theta1 with the superscript k and theta2 with the superscript k. Nambla j of theta with the superscript k is the gradient of the cost function evaluated at theta k. We simply propagate this iteration recursively starting from some initial guess of theta k, which can be, for example, a random guess. Before we introduce and explain the Python codes, we need to provide the answer to the following question. What is the physical motivation behind the batch gradient descent method? For that purpose, let us consider this figure over here. Theta1 and theta2 are the optimization variables. This magenta circle represents the level curve of our cost function. Any point, for example, this point, theta k, is actually a vector in this plane, and we can evaluate the value of the cost function at that point. For example, if this is a three-dimensional representation of the problem, this is, for example, theta1, this is theta2, and this is the value of our cost function, j. This point over here, that's represented in 3 dimensions over here, corresponds to the value of the cost function, j of theta k. In my previous tutorial, whose link is provided in the description below this video tutorial, we learned that the gradient vector that's shown over here points to the direction of the maximum and the fastest increase of our cost function. So if from our current point, theta k, we move in this direction with a small step, we will maximally increase the cost function. However, we don't want to do that. We want to go in the opposite direction. That is, we want to go in the direction of the maximum decrease of the function. Keep in mind this fact. Gradient points to the direction of the maximum increase of the function. Negative gradient points to the direction of the maximum decrease of the function. So we want to go in that direction. Perfect. Then we simply take the minus sign of our gradient and we obtain this red arrow that you can see over here. So this red arrow is a negative gradient. However, we don't want to take large steps when we perform optimization. So instead of going all the way here, we will scale our negative gradients by the step side or by the learning rate gamma, and consequently we will end over here. This is our next point for the next iteration, and this defines theta k plus 1. The iteration again is theta k plus 1 is the current value of optimization variables plus, and I deliberately put a minus sign over here, gamma nabla j theta k. And this is the main idea of the gradient descent method. We expect that the value of the cost function at the iteration k plus 1 will be smaller than the value of the cost function at the iteration k. And this is the direct consequence of the fact that minus gradient points to the direction of the maximum decrease of the function. Next, let us compute the gradient of our cost function. And here, for clarity, I will repeat the cost function. It's a sum when the index I goes from 1 to n, and I have yi minus theta 1 xi minus theta 2 squared. Here's the gradient of the cost function. I take the first partial derivative of my cost function with respect to the first parameter theta 1, and obviously as the result I obtain this expression over here. Then, if I repeat this procedure and I take the partial derivative of j with respect to theta 2, I obtain this expression over here. Next, I can nicely write this expression by introducing the error. The error is simply yi minus theta 1 xi minus theta 2. And by substituting this definition in the equation 30, I obtain the equation 32. And the equation 32 is very easy to be implemented. Let's next explain the Python implementation of the batch gradient method. Here, it's important to emphasize that these codes are provided on my GitHub page, whose link is provided in the description below this video. Also, these codes are presented on my website, and you can see codes are presented over here. As you can see over here, I'm using the Spider Python environment. The first step is to import the necessary libraries. The first library is the NumPy library, and the second library is the plotting library. So let's execute these code lines and let's import the libraries. Next, I need to select the true values of my parameters, theta 1 and theta 2. I simply assume that theta 1 is equal to 2 and theta 2 is equal to minus 2. Next, I need to generate the data. That is, I need to somehow emulate this equation. Or better to say, these equations. I do that over here. I take theta 1 true, I'm multiplying by x, then I take theta 2 true, and I add a measurement noise. Here you can play with the measurement noise, you can increase or decrease the measurement noise. Let's see what happens when I leave the measurement noise variance equal to 0.01. Let's plot the data. Okay, so here's my data. The data is perfectly linear, and you can change and play with this data set by increasing the variance of the measurement noise. Let's see what happens if the variance of the measurement noise is relatively large, then you have noisy data. However, since I want to illustrate the convergence of the method, I will keep the measurement noise relatively low. After these code lines are executed, we will have two vectors. We will have this vector, the vector of x values, and we will have another vector, the vector of y values. These vectors, or better to say, the entries of these vectors, are x1, x2 until xn, and y1, y2 until yn. The next step is to define two cost functions. The first cost function will return the gradient of the cost function for the current value of the theta vector parameter and for the values of the data batch vectors, x values and y values. And here is the cost function. I simply implement this equation. The code is straightforward. First, I form this vector, then I form these two values, I initialize them to 0, then I form my vector error, or better to say the scalar error, and I simply, in this iteration, update the entries of the gradient vector, the first entry and the second entry. And this code will produce this vector. That is, if I provide an input theta, and if I provide x and y vectors of batch data to this function, it will return the value of the gradient at the particular theta. The next function that we need to define is the function that will return the value of the cost function for the current value of the theta vector. Simply, I take theta vector, I take my x and y batch vectors, and I simply form the cost function that's shown over here at the beginning. Next, I need to select the batch gradient descent parameters. I select the number of iterations to be equal to 1000. This means that I will propagate this iteration 1000 times, starting from k is equal to 0, k is equal to 1, until k is equal to 1000. Next, I need to select the step size, gamma. In my case, this is a relatively small number, and I need to select the initial value of optimization variables. I simply assume an initial value to be equal to a random normal number. That is, the entries of theta 0, that is, the entries of theta 0 that are equal to theta 1, 0 and theta 2, 0 are random normal numbers. The next step is to initialize the vector of optimization variables. Theta current will be the current value of my optimization vector, and I set it to be equal to theta initial. To just emphasize this, theta current is equal to theta with a superscript k. And in this iteration over here, that is in this for loop, I update this vector by using this equation. That is by using the batch gradient descent method. And the implementation is pretty much straightforward. I also have two lists that track the convergence of theta 1. The first list is theta 1 list, and the second list tracks the convergence of theta 2, and I also track the convergence of the cost function. This is a good practice when developing algorithms and when debugging algorithms, to always track the convergence of the algorithm. So let's run this, and let's show first of all the convergence of the cost function. You can see here the convergence, and the graph over here shows the convergence of the cost function. This graph is also shown on my website, and it's given over here. We see a very nice convergence, so after maybe 400 iterations, we converged. However, we also need to see the convergence of our parameters theta 1 and theta 2. To do that, I will simply execute these code lines, and these code lines will print the convergence of theta 1 and theta 2. And here's the graph. I start from random values of theta 1 and theta 2, and I see that I converge relatively quickly to the true values. Keep in mind that the true values of theta 1 is equal to 2, and the true value of theta 2 is equal to minus 2. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.